It's just another problem, another day. What else can I say? This is 2855 minimum right shifts to sort the array. Okay. So you're given a zero indexed array nums of length n containing distinct positive integers. Okay. Return the minimum number of right shifts required to sort nums and -1 if that is not possible. A right shift is defined as shifting the element at index I to index I plus 1 for all indices. So, you take this array 3, 4, 5, 1, 2, for example, and how long is it going to take to make this sorted? Well, after one shift, everything shifts right. So this 2 gets shifted right off to the side, and it kind of revolves back to the front. All right. Then this 3 goes 1 to the right, 4 goes 1 to the right, 5 goes 1 to the right, 1 goes 1 to the right. We shift again. The 1 goes, the 2, the 3, the 4, the 5. Do you see that? So this 2 got shifted right here. This 3 got shifted 1. This 4 got shifted 1. This 5 got shifted 1. And then we do it again. And you notice, voila, you have the finished product here, right? The sorted array. So it takes 2 operations, right? It started as this. I did 1 operation to shift it like that. And I did another operation to shift it like that. So, well, there's kind of really only 2 things you need to consider in this problem, right? The first thing is can it be sorted? And the second question is, how long will it take? Okay. Now, how do you know if something can be sorted via right shifts? Well, for example, this can't be sorted during right shifts, and why is that the case? This is an example of something that can't be right shifted in order to sort it. That's why we return -1. Well, the reason why that is right is, well, you can right shift once and you'll get 4, 1, 2. Okay, that didn't work. Or no, that's not even what you get. What is wrong with me? 4, 2, 1, right? You right shift again. Maybe you say, okay, I'll right shift again. I'll right shift again. I think that's the best thing I can do here is right shift again. So you get 1, 4, 2. You're like, okay, that doesn't work. So then I'll try shifting again, and I get 2, 1, 4. And now we're back at where we started. So why doesn't this work? Well, right shifts, right, only will move things relative, right? Because everything kind of still stays together, right? You're just shifting everything over, but it's not like you swap anything, right? You're just shifting. So the relative order stays the same, and you're just trying to take this relative order of an array and shift it over to make it work. So what does that really mean? That means from the minimum, it has to increase up into the maximum, but it might wrap around. Right here, from the minimum, it increases to the maximum. You see what I'm saying? It goes from 1 to 2 to 3 to 4 to 5. Right? And no matter what orientation it's in, right? From the minimum, from the start to the end, starting from the minimum to the maximum, it needs to increase, right? The problem here is from the minimum to the maximum, it doesn't keep increasing, right? It goes from 1 to 4 to 2. Now, so not from the minimum to the maximum. Maybe that's not the best language, right? For the length of the array, starting from the minimum element, it needs to be increasing, right? So this array has length 5. So starting from 1, it needs to be increasing the whole way for it to be sorted, right? So from 1 to 2 it is, from 2 to 3 it is, from 3 to 4 it is, from 4 to 5 it is. Here, the length of the array is 3. So from 1 to all 3 elements, it needs to be increasing, right? So from 1 to 4, it is increasing, but from 4 to 2, it's not increasing. So that's why you would return -1, because it's impossible, right? I can't swap elements. I can only change, I can only kind of like, shift it. So since I can only shift it, there's really nothing I can do here in terms of, trying to make this thing sorted. It can't be sorted, right? It has to be sorted with respect to the position of the element, right? So can it be sorted? Well, the answer to this question is, well, is it sorted already? Just shifted. So only if it's sorted, shifted. So what I mean by that is like this thing is shifted, sorted, right? This thing is shifted 3 to the right, I guess, or 2 to the left, however you want to look at it, but it's still sorted, right? 1, 2, 3, 4, 5. If I can go straight and loop around and keep going straight and it stays sorted, then we're good, right? This thing is not shifted, sorted, because it goes 1, 4, 1, 4, 2, right? It needs to go 1, 2, 3, 4, 5, not 1, 4, 2, right? You see this downward motion here I'm doing with my hand? So that's not going to work, right? So it has to be shifted sorted. And the way that you can discover something shifted sorted is you start from the minimum and you just kind of walk your way through. And if you ever find something that goes down when it needs to be going up, then you know that it's not sorted. And how long will it take if it is, right? If this condition is true, how long will it take to sort the system? Well, these are right shifts, right? So to get one, the minimum element needs to be in the first position, right? Whatever your minimum element is, at the end, it needs to be here, right? This element, that's the minimum, is the minimum, so it needs to be at the very beginning of the array if it's sorted, right? The smallest thing is the leftmost element. So what does that mean? Well, how are we going to take one and get in that position? How long is that going to take? Well, I'm right shifting. So that means I have to shift 1, 2 elements away, right? So I have to shift twice to get this thing over here. So how does that work? Well, whatever position I am, I'm the length of the array minus that position away, right? Because I have to keep going right until I get to the front. So that means I have to go 1, 2 elements forward. So the length of this thing is 5, right? And the position of the minimum is 0, 1, 2, 3. And the answer ends up being 2, right? So, but that's just the distance away from the right. So when I go right, I need to go back to the front. So that's just length of nums minus the position of the minimum element, which equals 2. So that's just what this answer is, unless it's already at the front, right? Because if it's already at the front, you don't need to shift at all, right? The worst case would be the elements right here, the minimum, and you'd have to go the whole way to get back to the front. Since you can't go left, you can only go right. You have to go all the way right until you loop back to the front, right? But if it's already at the front, you don't need to do anything. So unless it's 0, right? If the position of the minimum is already at 0 and it meets this condition, then it already works, right? So we have to go right to loop back around to get minimum element in position 0. All right. So that's just the length of nums minus the index of the smallest element. All right. All right, so with that said, let's go ahead and just solve this problem. All right. So what we really need is we need the position of the minimum element first, right? So we'll say index equals the min range length of nums, key equals lambda, index nums index. All right. So what we're doing here is we're basically saying we're going to look at all the indices, and we're going to find the minimum such element and return that corresponding index, right? So if we print index here, right, for this example, the index is 0, 1, 2, 3. So we should see 3 here. So you can see that this works. 3. Okay. Now we want to check the first condition, right? We want to ensure that this thing is relatively sorted. So let's do that first. So we'll look at each offset. So it has to be increasing from the minimum for the total number of elements that there are, right? Now we should probably start at 1. So what does it mean for it to be increasing? That means that we have to have it be the case where nums at index is greater than nums of index minus 1. So I'm going to do an offset here. So we'll start at the minimum, right? And then we'll basically say plus 1. So we'll look at each subsequent element and say, is this element larger than the previous element, right? It has to be, everything has to be larger than the previous element. I guess larger than or greater than or equal to, even though they're distinct. Let's just do this because, you know, maybe another problems aren't distinct. So there's nothing wrong with being greater than or equal to here. But technically you'd only have to do greater than because all the elements are distinct. Okay. But with that being the case, we say, all right, is this element larger than the previous element? And we have to do that for the whole array, right? The problem here, though, of course, is that, what's the problem here? The problem here is that, you know, we're going to be, since we're going all n, we need to have some sort of mechanism to wrap around, right? So to wrap around a string or wrap around anything, right? If you modulate it by the length of nums, that'll bring you back to the front, right? So you'll go 0, 1, 2, 3, 4, 5. If the length was 5 or 6, and then it would go back to the front to do that. So if you ever want to wrap around a string why do I keep saying string? You ever want to do a wraparound operation to stay within the boundaries of a system? You modulate it with the length of that system, right? Because what we don't want here is like we compare 1 to 2, and then we want to compare the next thing, right? But we need to increase this, and you know, there's no elements here, so you can go outside the boundary, right? The next thing you really want to check is 2 to 3, then 3 to 4, then 4 to 5, right? But we're offsetting, so we want to keep it within that boundary by using this modular operation, right? So maybe I'll print out, you know, what's happening here so we get a better idea of what's going on. Sorry, someone's calling me and it's annoying me, but that's okay. All right. All right, so so you should see, you know, it compare, right? So we compare 2 to 1, then 3 to 2, then 4 to 3, then 5 to 4. So hopefully that proves to you, you know, that this system works, right? And you should probably, if you don't understand this modular operation, then you probably shouldn't, I mean, to be honest, you probably shouldn't even be approaching Leetcode problems yet, because it's a pretty fundamental operation you need to understand in programming or just in simple mathematics, right? But basically the idea of modularization is it gives you the remainder, so it just keeps you within a range. So if you overshoot the range, it wraps you back in, right? And a good example is a clock, right? A clock, if you have a 12-hour clock, right, a circular clock, hour 13 is really 1 p.m., right? You know, 1 a.m., 2 a.m., 3 a.m., 4, 7, 8, 9, 10, 11, 12 a.m., 1 a.m., right? So plus 13 still keeps you within that system. It gets you back at 1. So this thing, when you go outside of the system, it just wraps you around back at the beginning. You can think of this as being kind of circular. Okay. So modulars always work with circular systems. So if this is the case, then we're good, right? So if this is not the case, then we're bad. We can't fix the system when we return -1. Okay. Now let's think about, what does it mean? So if we get through this whole thing and it doesn't return -1, that must mean it was sorted, just, you know, relatively sorted, shifted. So we need to figure out, well, how far do we need to go? Well, we go length of nums minus the index, if the index exists, else it's already at position 0. So if index, I'll just do this so it's not, else we return 0. And that's it. All right, guys. So for this problem, I'm going to talk like it's going to be good. Okay, it's good. So what is the run time and space complexity? So let's say n is the length of nums. All right. For time, well, we have to find the minimum element. So we have to look at all the elements to figure out which one's the minimum, right? There's no escaping that because it's not sorted or anything, or it is, could be sorted, maybe, no, maybe not. So that's going to take n time. And then we have to look at all the elements and ensure that they're relatively sorted, just shifted. That's going to take n time. And then we just do a constant operation. So it's n operations, 2n operations, big O of n operations. Okay. How about for space complexity? Well, we just create this index that's constant space. It doesn't matter how large nums is. We're just going to find the minimum element. And then we just determine by making comparisons. We don't even set any variables here. And then we just return a constant variable representing the number of shifts we have to do. So that's constant space. All right. Now for this problem, I mean, it is an easy. Maybe it could be classified as medium. I don't know. But, you know, the constraints are so small, you could actually probably do something that's way less inefficient and still get the answer. Maybe like sort the system first and then compare each element individually. I don't know. But, you know, you have a lot of leeway in terms of what you're able to do because the constraints are so lax, so relaxed. All right.